Hello guys, good evening, a warm welcome to my sessions. Today we are going to take a look at Hess's Law. This particular law is essentially a corollary of, law of conservation of energy, law of conservation of energy. The word corollary essentially means a direct result. It's a direct result of the law of conservation of energy. And the statement basically says the enthalpy change is same irrespective of delta H is same, or enthalpy change is same irrespective of whether whether the reaction is carried out in a single step or multiple steps. Yeah, so let's go through these statements again. It's essentially corollary of law of conservation of energy, which essentially means it follows directly from law of conservation of energy. And also the statement is that delta H, or the enthalpy change, is same irrespective of whether the reaction is carried out in a single step or in multiple steps. Well, we will now understand this through an example. And essentially, Hess's law is very similar to vectors, the application of vectors. So let's say we want a reaction wherein, let's say, A transforms into B. So there is a reactant A which transforms into B. So this is a direct route of going from A to B. And then let's say we have an indirect route also. So where we first go to C and then from C we move on to B. So this is an indirect route of bringing about the same change. And as we know from the vectors that AB vector is essentially AC vector plus CB vector. So you'll see that Hess's law essentially makes the same statement. So what it says, if the enthalpy change here is delta H1, over here it is delta H2, and over here it is delta H3, then one can safely say that delta H1 is equal to the sum of delta H2 and delta H3. So we can draw parallels between these two, the vectors relationship, triangle law of vectors to be more specific, and the Hess's law. Now the question is why this is so. Why is it important to have this kind of relationship? Well, if this relationship is violated, then it will lead to a perpetual machine. So for example, if let's say we have delta H1 equal to, let's say, 300 joules, delta H1 equal to 300 joules, and we have delta H2, let's say, equal to suppose 50 joules, and we have delta H3 equal to, let's say, 150 joules. So let's say these are the figures, and essentially if we put let's say these are negative values, negative in the sense these are exothermic processes. So now the deal is that if we move directly from A to B, then the total amount of energy what we are going to get is 300 joules. When we move from A to C, we are going to get 50 joules, and when we move from C to B, we are going to get 150 joules. So delta H negative essentially means an exothermic reaction. So this is what we are going to get in these figures. Now the thing is that over here, if we see that this figure is different from the sum of these two figures, and this will allow us to design a perpetual machine. तो हम एक perpetual machine को build up कर सकते हैं. What we can do is we can move from A to B, and then we take the reverse path from B to C, and then we'll go from C to A. And now during this journey we got 300 joules of energy. From B to C we'll be spending 150 joules of energy, and from C to A we'll be spending 50 joules of energy, in the sense that this figure is plus 150, the journey B to C, and this particular journey would be involving plus 50 joules. So that means if we just continue along this cycle, we will always make 300, so this much plus 150 and plus 50, and that boils down to minus 100 joules. So that means whenever we make this anti-clockwise cycle, we will be able to make or derive 100 joules of energy, and there is no net change during this entire process, which essentially means it's a perpetual machine. So every time we'll complete a cycle, we'll be able to generate 100 joules of energy. And this is simply not possible. We cannot have a perpetual machine which generates energy out of nothing. And hence, what we ought to have is a parity between the energy over here and the energies over here. So, the kind of figures we should be looking at would be something like, let's say, so if this was something like minus 250 and then this is minus 50, then we'll see that during an entire cycle, we'll not have any net energy generation, or in other words, the law of conservation of energy will not be violated. And this directly implies that this particular sum, this particular energy has to be equal to the sum of these two always. Otherwise, it will allow us to create a perpetual machine. Well, now to summarize this, the easiest way to memorize Hess's law is to think in terms of vectors. So if we have a change A to B and we can apply the triangle law of vectors, so this particular leg is equal to the sum of these two legs. So coming back to the statement, the enthalpy change during a reaction is same whether the reaction is carried out in a single step or in multiple steps. So I hope this makes Hess's law a bit clear, what this is all about. Now let's see its application in terms of Born-Haber cycle. Born-Haber cycle is frequently used to calculate the lattice energy, because lattice energy is not possible to be calculated directly. We just cannot calculate lattice energy directly. So we'll now learn the application of Hess's law in Born-Haber cycle. So let's say we want to calculate the lattice energy of a salt, which is sodium chloride. तो हमें सोडियम क्लोराइड की लैटिस एनर्जी चाहिए, which essentially means that if you take 1 mole of solid sodium chloride, then how much energy is required to dismantle it into the corresponding constituent ions. So what is the amount of energy? The amount of energy which is required to dismantle this solid ionic compound back to its individual constituent ions in the gaseous state. This is what is referred to as lattice energy. Now, we have to separate them infinitely as per the requirements, like there must not be any force of attraction between these two. And since that is practically impossible, it's not possible, it's not feasible to calculate lattice energy directly. So therefore now, we will look at an indirect way of arriving at the lattice energy using Hess's law. So here we go. So we need the lattice energy for sodium chloride. So our first process will be to create sodium chloride, the formation of sodium chloride using this process. So we end up getting NaCl solid, and this particular energy is referred to as enthalpy of formation, delta HF. This is enthalpy of formation of sodium chloride. But then, since this is direct process, we can always go for the indirect ways also. We can make sodium chloride in an indirect way also. हम indirectly भी बना सकते हैं. So what we can do is we can take a different journey. So sodium can be first vaporized to sodium vapor. So this is sublimation process. So delta H sublimation, and this converts to gas. Similarly, we can split chlorine molecules into chlorine atoms. So this is delta H dissociation. And here we get chlorine atoms in the form of gas. Then we can ionize sodium atoms, so we can remove the electrons and we end up getting sodium ions, so again in the gaseous form. And whatever electrons we have removed from sodium, we will pump those to chlorine atoms. So chlorine atoms gain these electrons, they accept these electrons and they transform into Cl minus ions again in the gaseous state. Now, let's allow these ions to combine together and form solid sodium chloride. So, as we know, this is nothing but the lattice energy. This is lattice energy. So, lattice energy, in this case, it is being released. It will be released. The reverse process of dismantling involves consumption of lattice energy. So, we need to evaluate the lattice energy over here, and now we can use Hess's law. So according to this particular law, what we are going to do is simply look at the direct way and the indirect way of arriving at the same thing. So which allows us to write this equation. Delta HF is equal to, or must be equal to, the sublimation energy, that is delta HS, the sublimation energy, plus the enthalpy of dissociation, And of course, there are enthalpy changes here. So this is delta H ionization, and this is delta H electron affinity. So these also have to be added. So plus delta H ionization plus delta H electron affinity and plus lattice energy. Plus lattice energy. So this is the equation which can be framed on the basis of Hess's law. So for the direct process, we have the enthalpy change delta HF, and for the indirect process, we have the enthalpy changes as sublimation, dissociation, ionization, electron affinity, and the lattice energy part. So the sum of these, all these has to be equal to this as per the Hess's law. So therefore now we have the figures. Let's see what all figures are available. We know this delta HF. Okay, heat of or enthalpy of formation of sodium chloride is tabulated. It's easy to evaluate. We have the figures for the sublimation also. We have the figures for the bond dissociation enthalpy of chlorine, that is well established. Ionization energy of sodium is well established, and the electron affinity of chlorine is also tabulated. It's very well established. That means in this equation we have only one unknown, which is lattice energy, and hence lattice energy can be easily calculated using Born-Haber cycle, which in turn is based on Hess's law. So this was one of the most well-known applications of Hess's law, and I hope this lifts the wheel of Hess's law and makes it easier to understand and grasp. And I hope you will appreciate my videos, and please leave any comments for further discussions on any intricate topic. I'll be more than happy to make a video on that. Thank you so much. Thank you for listening. See you.